Okay, we've got a quiz problem here, but just to put this into context, in the context of what we did in lab last time and some of the stuff that we observed. Remember, if we substitute A equals F net over M into the equation of uniformly accelerated motion that expresses the definition of constant acceleration. Constant acceleration is change in velocity over the time, right? So if you rearrange that, change in velocity is VF minus V naught. Divide that by T and you get A. You multiply by T, you get AT. And then you add the V naught to both sides and you get this, okay? And that should be second nature. We should totally understand that. And we should have used that numerous times in solving problems, okay? Because that's the way we learn it. I'll comment that, I've been trying to upgrade my knowledge of quantum mechanics by reading and working things out in my head and understanding the principles and so forth. And I look at the problems, but I don't write them out because I just want to see if I'm capable of doing that at the level I'm working at. And I'm finding that I keep forgetting things that were obvious to me a week ago. It's because I haven't actually written them out in solving the problem. Okay, the act of writing it out, and even better, if I had somebody who really wanted to know it, being able to teach it. But we don't have the opportunity to do that. We got to solve problems, analyze lab situations, analyze thought experiments, and so forth. So it's all one of a piece. We read, we work problems, and we then go back and look at what are the principles behind what we do. Okay. So anyhow, that's why we're talking about this. Okay, we take this equation and we plug in the definition of acceleration. It's not just equations, it's not just symbols, it all has meaning. So you don't want to think about the meanings, but what we do get very quickly is that F net delta T equals M delta V. That's the impulse momentum theorem. Okay. And really it should be average F net times M delta T equals M delta V. Okay, there's a differential expression of it too. So differential expression is F net isn't constant, or that actually integral expression differential too. But F net delta, the integral of F net delta T is M delta V, where the integral is taken over the time interval during which the two masses or two objects are interacting. Okay, now we have an example of that here that we're working out. We want to put it into this context. This comes down to F net average times delta T equals M delta V. Okay. If we have a constant net force in the delta T, this works. In general, the average net force times delta T equals your M delta V. And this even assuming that M is constant. M doesn't necessarily have to be a constant. And then it would be the change in MV, which is M times a change in V plus V times a change in M. Product rule. Okay. So anyhow, if you know the average F net in the time of interaction delta T, you can find delta V very easily. Well, we did that last time, we talked about it. And we see that if you have a given delta V, given M delta V, okay, and you know the delta T, you can find the net force, which is what I'm asking you to do over here. Okay. Just another quick comment before we dive into this. Remember the whole picture? Everybody understood it pretty well. If you have a force versus position graph for a conservative force, and this is a graph that pretty closely models force between two magnets, and where my two magnets go, I can actually hold them up with it. Now, this is relevant to the preceding chapter, but I want to do this before I wash the board. Okay, so I push these together. Okay, now they're at a proximity of about 3 centimeters. What's their potential energy? If I release them, how much kinetic energy is going to fly out of this thing? Okay, we can get an answer from this graph. Okay, now this is proximity in millimeters. 3 centimeters is right about here. Okay, what's the average force times your delta X, at least between here and here? And maybe even extrapolating out to where the force becomes negligible, where the integral of the force times your X from here to infinity would be negligible. Okay. And we're pretty close to it here, but there's still a little bit left. Okay, so anyhow, it looks like the average force over the interval from 3 centimeters out to at least 64 centimeters would be somewhere in the neighborhood of the weight of force of gravity on about 34 grams. We multiply that 34 grams times G, okay, and get like somewhat a little over 30,000 dynes. You know what dynes are, and multiply that by the distance, and then convert your units to get units of ergs or units of joules. Okay, so it'd be fairly easy to do. Okay, now I'll be asking you to do things with this and with your own data. Probably not until after the test, but you ought to think about it in terms of the test, because I could ask you a question about this. I could give you numbers, ask you to construct the graph, and figure things out. What's your change in potential energy between here and here? Okay, or construct a graph of your potential energy from the graph of your force. Of course, you've got a formula, it becomes easier because you can always integrate. As long as you got something you can use. Okay, well, that's a digression, a little bit of a digression. I don't want to do that because we'll have to wash up the electrical. Okay, now let's go to this. Okay, I have done the homework and so forth and read. You should be well equipped. What's the definition of momentum? It's mass times velocity. Not mass times speed, it's mass times velocity. So velocity has signs. Okay. And what we have here, if it's mass times velocity, look at what we've got. We've got masses and velocities. Now, I've got arrows in these things. So I've just got speeds here and directions. Okay. So if you consider this to be the positive direction, then you have a positive velocity here and a negative velocity here. These things are approaching. Of course, this could be moving at 5 meters per second in that direction. If I had the arrow in that direction, this thing would catch up to it and they would still interact and you'd have collision. Okay, rear end collision as opposed to head on, which is probably better. Okay, makes sense. Okay, now we have velocities before and after collision. But we have all the information we need to calculate the momentum of each object before collision and after collision. So we can answer the questions I posed. Well, how much is the total momentum change? Well, it doesn't change. If so, by how much? What about kinetic energy? Does it change? If so, by how much? And then if the collision lasts 0.02 of a second, what's the average force of the 4 kilogram mass on the 3 kilogram mass? Yeah, well, This question really quick and easy to answer once you get the signs right. So we'll answer them. But first, let's talk about this, because what we introduced is the impulse momentum theory. And at least one of you, I think, is working this before the others. I could be wrong, but that's fine. Just, that's a thing that would not surprise me if you, at this point, you understand better than the other, although this is really easy because you know what momentum is and what kinetic energy is, you calculate it and figure out whether it changes, okay? So it's very easy to do this, so we'll come back and do it. But down here, let's talk about this. Okay, so I'll do F net bar delta T equals M delta V. What are you trying to find in that force? If you're going to use this to find the net force, well, you're going to need the mass, you're going to need delta V, and you're going to need delta T, right? Okay. So what's the mass? Okay, so to answer the question, which mass are we going to use here? We're trying to find the force of the 4 kilogram mass on the 3 kilogram mass. So that's a force on the 3 kilogram mass. So we're going to use 3 kilogram mass, the change in momentum with 3 kilogram mass. So that's going to be or put numbers in, let's say it's M times its final velocity minus M times its initial velocity, right? Which is, of course, change in P over change in T. Okay, so let's write that. Just a little note. This is delta P of the 3 kilogram mass. We're going to write it not too many subscripts, and we want to understand that. So that's what M 3 kilograms times 25 meters per second minus 3 kilograms times negative 5 meters per second. We divide that by delta T. Of course, we know delta T, so I should have just written this quantity. 0.02 seconds. So what are we going to have? We're going to have 25 kilogram meters per second minus a negative 15 kilogram meters per second, which is 40 kilogram meters per second. So don't have a lot of room. It's 40. Kilogram meters per second divided by 0.02 seconds, which is going to be 2,000 newtons, which is pretty close to 500 pounds. Okay. If the time of interaction had been 2 milliseconds, 0.002 seconds, it'd be more like 20,000 newtons or 5,000 pounds. Okay. And you can have forces like that very easily in a collision. We talked in lab about, well, depending what the material is here, how much of these things compress at this relative speed to get an estimate of how long they're going to be in contact. If it's 2 steel blocks, they aren't going to compress much and you're going to have a collision in the millisecond range. or less. Okay. If it's two Nerf balls, they're pretty spongy. That interaction might take half a second. Probably not that much, but because they're also very light. But, or if the interaction is magnetic. This thing has a magnet in front, this thing has a magnet in back. Okay. Or two magnets facing each other. Yeah, that interaction could go on for a long time. That interaction actually goes on forever because the magnetic force is there at any separation. It becomes negligible fairly quickly, so we just have an approximation. You got that to worry about. If they have springs, two of these carts that we used in lab, and there's a spring there, you turn it over and see the spring. Okay, then the springs compress and go apart. You could use Audacity to listen to that interaction, and you probably see in the waveform the noise made by the spring. Okay. Now, if you had a remote microphone attached, to the thing where you could really hear the spring squeaking around and stuff, doesn't squeak much, pretty good spring. You might be able to determine how long that thing goes, but you can pretty much tell by how far it compresses and how fast it was going, how fast the blocks or the carts were going. And we talked about that in lab. You want to think about that. Okay, if they compress a centimeter and their relative speed is a meter per second, then it's probably 100th of a second interaction, maybe 2 minutes. What to think of it? Okay. So that's how we use the impulse momentum theorem. Now, we can also incidentally find force of a 3 kilogram mass with a 4 kilogram mass. That's written kind of small, the chunks goes solid. F net of the 3 kilogram on the 4 kilogram mass would be kilograms. Its change in velocity. Now I wrote out the mvf minus mv naught to be sure we understand that's a delta p over delta t. We don't really need that reinforcement now that we've seen it. So we can just go to the m delta v. What's delta v? Goes from 8 meters per second to negative 2 meters per second. And that's a negative 10 meter per second. Well, that equals negative 2,000 newtons. Well, how cool is that? That worked out the same as equal and opposite to that. Darn well better be equal and opposite to that, because Newton's third law says it should be, and Newton's third law is part of the way we derive the impulse momentum theorem. Okay, so if we derive the impulse momentum theorem correctly, we had better get the same result. Okay. Okay. Now, let's let this be the first pass. Total momentum before collision. First mass, 8 meters per second times 4 kilograms, 32 kilogram meters per second. Second mass, 3 kilograms times -5 meters per second, negative 15 kilogram meters per second. You want to write out more detail than that. Want to connect it back to definitions and so forth and understand that the definitions come right out of our derivation of the impulse momentum theory. On one side, we get m delta v, which is m1v1 plus m2. Well, anyhow, okay. Out of the impulse momentum theorem, we get the idea that mv is what we want to call momentum, and f delta t is what we want to call impulse. Okay. Okay, so there we have it. After totals again 17 kilogram meters per second. So this is a possible collision. If I had screwed up a little more and had impossible numbers here that don't match numbers here, then our assumption that this is an isolated collision, okay, an interaction of two forces isolated from the rest of the universe, where the net force is just the force of interaction. We have contradicted that. If the total momentum before, total momentum after had not been the same, we would know that there are additional forces. If the interaction force is not the only thing that's going on. Okay. In terms of what we did in lab, we had those two carts on low friction carts, so we can assume that friction's negligible, although it's not really so, on pretty well leveled incline. Leveled it by rolling the pool ball back and forth and seeing if it acted the same in both directions. Okay. So it was pretty well leveled. And it's pretty low friction. And it's pretty straight, but I don't think it's totally straight because of some of the things that happen. So there are little discrepancies. So there are little bits of force that aren't just interaction force. If the thing's tilted one way or another, then you got a little bit of gravitational force. Okay. The friction is there. It's pretty low, but it's there. So you wouldn't get perfect results, but you probably get pretty good results. Everything I did was calculations I did in my head. Everything is pretty close. Okay. So again, assuming you have an isolated system, everything is consistent with the idea that this is an isolated system. Momentum is conserved if you calculate the net forces. They come out equal and opposite. Okay. All that needs to be so. Now, what about kinetic energy? Does kinetic energy have to be conserved? No. Okay. Two objects can come together and come to rest if they have the right combination of masses and velocities. And they certainly don't have any kinetic energy when they're at rest. Okay. And they certainly do have kinetic energy when they're approaching each other. They might have equal and opposite momentum. In fact, if they come to rest, they do. But they don't have to have the same kinetic energy. And that's the difference between an elastic and an inelastic collision. If it's elastic, total kinetic energy stays the same. That means they would collide and spring apart with the same relative velocity. That's coming up. Okay, well, kinetic energy Total kinetic energy is 1/2 mv squared. V squared here is 64 meters squared per second squared. Half of this gives you 128 joules. Okay. This gives you half of 75 joules, which is 37.5 joules. And I like adding 128 and 75, it's easy to deal with that half. You get 203, so you get 101.5 joules if I did that right in my feeble brain, okay? Put a little question mark there. You can calculate that, just 1/2 mv squared and 1/2 mv squared. Afterwards, could be easy, the numbers are small, but we got a dang fraction up there, so I guess not, but okay. I don't know why I do this myself. You get 4 meters squared per second squared. Half that being 2, that's 8 joules. Okay. Here you've got 25 thirds, you square that, you get 625 ninths. Multiply that by 3 joules, you get 625 thirds. Half of that, 625 sixths. I think that's going too fast. 625 over 6 is already more than 105 joules. 625 divided by 6 is 104 and a sixth. So you get 112 and a sixth. Now I've got to check that out. That's about 8 meters per second. And that can't be right. Because if I square 8 meters per second, I get 64 meters squared per second squared. It's a little more than 8, so just promote that up to 20 instead of having to do all the things that confuse me, gave me the wrong answer here. Okay. So it's around actually, whoa. That's 8 meters per second. You're going to get 64. 32 times 3 is 106. That might be close. Looks like we do have too much kinetic energy, but that can't be. So I must have done something else wrong. And now, why am I puzzling over? Puzzling over, first of all, whether we've gained kinetic energy. And when I do these calculations, let's do it again. Let's say that's 70 meters squared per second squared. Half of that's 35, and you multiply it by 3, you get 115, which is more than I got there. My numbers aren't right. Makes me wonder about my numbers here because 64 times half of that's 128. Wait, I got 128. Okay, I know what I did. I did something wrong. Okay. Pretty clear to me that the kinetic energy of this after collision is less than this because this is only going a little bit faster, but it's not that much less mass. Okay. So this is more mass moving almost as fast. It's going to have more kinetic energy. This is almost this much mass, moving it over twice the speed, and you're going to square the speed. So you're going to get more kinetic energy here than you got here. My mistake here was I had the 128, but I took half of that when I did this. And that's going to be 37 and a half, 128 and 37 and a half is 165 and a half. I think. Maybe that's right, and maybe this is right, but now it makes sense. Okay, now the reason I don't mind messing around with that in front of you because you want to think about these things. The kinetic energy afterwards cannot be greater than the kinetic energy before unless there's been some release of potential energy or some external force. I'm pretty sure there's no external force because momentum's conserved. If momentum is conserved, that means maybe one of these masses had a coiled spring that got triggered to uncoil at the instant of collision. So maybe there was potential energy in here that was hidden. In that case, we didn't really have an isolated system. There was excess potential energy, and there's a change in potential energy. Whether that's an isolated system or not a question I want to get into right now. Okay. So all that comes out of this simple example. A lot of principles there. Okay, so once again, we have a collision depicted here. Velocities V1 and V2, masses M1 and M2. Before collision in white. After collision, velocities U1 and U2. And the angles of the after collision velocities with the x-axis are theta1 and theta2. And what's the total momentum before collision in terms of V1 and V2? After collision, in terms of U1, U2, theta1, theta2, all in terms of I and J vectors. So write them out with I and J vectors. Okay. So, what express the total momentum in terms of V1 and V2? Well, the first thing we have to do is say that V1 equals the magnitude of V1 times the I vector. Now I'm going to write this out. There are various ways to write it out. I'm going to use P1B for the momentum before collision. Momentum of the first mass before collision. And that's going to be M1, V1, I. Very simple. Okay, and then V2 is magnitude of V2, both in the negative y direction. The I vector is in the positive y direction. So the negative, the J vector is in the positive y direction. Okay, maybe I said. And the negative J vector is the one in the negative J direction. So you have to express V2 is V2 times negative J. So P2 before collision is negative M2 V2 times J. If you multiply M2 by V1 times negative J, that's what you get. Very straightforward. Now it's a little less straightforward when you got angle. Y'all did pretty well with the angles. Maybe not completely. You've got to see the things you got to be careful about, but your trigonometry looks pretty good. So after collision, now we have to specify what we mean by these angles. There are two ways we can measure the angles with respect to the x-axis. Either from the positive x-axis all the way around, or from the nearest angle to the x-axis, okay? But it's got to be with respect to the x-axis. So you're going to get a different expression than somebody else who did it differently. It's all going to come out the same because, like if you do the angle with the positive x-axis, you're going to have 270 degrees plus whatever you get if you just measured it from here. It's all going to be consistent. It's just going to look different. Okay, well, Let's look at it. I'll draw a picture. Just the velocity vectors. And I'm going to say here's theta 1. And here's theta 2. Okay. If you did it from the axis, that's okay too, because the expressions are more straightforward. I didn't specify just how these angles were defined. So you could assume either way. If you assume this way, though, see that U1, if that component's actually sprawled out. Here's U1. And here are the components of U1. So we're going to cross out U1. And we're going to say this is U1 cosine theta times I. And we're going to call this one here, this is U2 sine theta times J, but it's got to be negative because it's down. Okay. And then here we have it, U2. Both the X and the Y components are going to be negative because that goes down into the third quadrant. Okay. So U2 is negative, U2. And this should be cosine theta 1 and sine theta 1. Cosine theta 2 I minus U2 sine theta 2J. Okay. So that P1A means P1 after collision. And since it's in purple, we know that it's got to be after collision. Some people don't like color coding. There's a point to that. I'm going to use color coding. Okay, so we got M1. Times this. So we distribute the M1 through here, and we get M1 U1 cosine theta 1 I minus M1 U1 sine theta 1 J. Now, similar for U2. You just look back at what U2 is, make sure you've multiplied M2 by U2. There you have it. Hey, take a good look at what I've got, see if it makes sense. Okay, now I have commented that if you measure all your angles from the positive x-axis counterclockwise, you don't have any negatives. Expressions are identical, but no negatives. But the negatives come out when you calculate the sine and the cosine. Here, you got to make the decision what's positive, what's negative. Well, in this case, it's pretty obvious. In many cases, it is. So 6 1, half dozen another, as far as I'm concerned. But my lab's going to generally do it this way. Many reasons, kind of like it the other way if you're careful. Whichever way works for you is fine with me. Okay, so now we know what? We know that the total momentum before it is a total momentum after. Well, it's pretty easy to write out the equation. That means you got M1V1I minus M2V2J equals this, okay? Step by step. You start out by writing your velocities in terms of the I and J vectors before collision. After collision, you got to worry about the sines and cosines, but that's pretty easy. Okay, especially if you've done a lot of them, it becomes automatic. So automatic that you stop thinking to do it wrong. So you got to be careful as well as automatic, but that's okay. Okay, and then we just set the total momentum equal. Total momentum before is this plus this, total momentum after is this plus this, there we have it. Okay, now, what do you do about this? Well, I've only got 2 minutes, so I'm going to kind of skip a step. But we want to start out the main point of the whole thing is that, okay, and we want to write it this way because what do we have over here? We have a multiple of I and multiple of J. They're independent. It's hard to set this equal to this until we see what the total I is. Then M1V1I is going to equal whatever the coefficient of I here is, it has to match the coefficient of I here. And of course, this all comes out because forces, perpendicular forces are linearly independent. And that's what it all comes back to. You want to maybe think through. Okay. And then we have again, I'm writing down what I see, which is what I really need to be writing down. I'm not looking at the right place. Okay. Okay. Now you kind of see the symmetry in these expressions. Okay, you've got a cosine theta 1, cosine theta 2, a sine theta 1, a sine theta 2, makes you think maybe I did something right. Let's see why that is. Okay, so you want to look at these patterns. That just helps you kind of check out and make sure you haven't done something wrong. Of course, you don't want to just write it down because of the pattern you think it's going to be. Write it down by what it is, and then see if the pattern is what you think it ought to be. Just a little advice on debugging your solutions. Something I'm an expert at because I screw them up so often. Okay. What does this tell you? The I components are equal, so M1V1 has to equal all this. And M2V2 has to equal negative M1 U1 sine theta 1 minus M2 U2 sine theta 2. Let's make sure all our M1s are with theta. M1s are with theta 1 here and here. All our M2s are with theta 2 because theta 2 has only to do with the second mass, right? Double check that. And now we have a system of equations that we can easily solve if we know enough information. So for example, if we know the speeds U1 and U2, that's all we need to solve for theta 1 and theta 2. If we know M1, V1, and M2 and V2, okay? We know the initial velocities. Now we know this and we know this. Okay. And if we know U1 and in addition, U1 and U2, we know this. So all we have are the unknowns theta 1 and theta 2. Okay. Now we've got a bunch of possible unknowns here. M1, V1, M2, V2, U1, theta 1, U2, theta 2, that's 8. We've got to know 6 of them. Maybe we don't know anything. We don't know. Okay, we don't know U1. We don't know the magnitude or direction of U1. And this is a common thing. If we know these velocities before collision, and we've, let's say, measured the motion of M2 after collision, then we know everything except the magnitude of U1 and the theta 1. Okay, so how does that look? Well, we don't know M1 and we don't know theta 1. That's just two things that we don't know. We know everything else. Okay. Or maybe we know M1 and V1, we don't know M2 and V2. But we have measured everything that comes out of the collision so we can figure out what went into the collision up here. Okay. 2 equations and 8 unknowns. We've got to know, or 8 parameters. We've got to know the values of 6 of those parameters in order to determine the 2 remaining. And there are many ways this can occur. And you have a lot of 2-dimensional collisions in your problem assignments. What they come down to is you can split the X collision and the Y collision. Okay. Everything is conserved in the X direction, everything's conserved in the Y direction. That's the bottom line. In this one model shows you pretty much everything you need to know to set up a collision problem in 2 dimensions. And it just comes down to 2 collision problems in 1 dimension, but they both got to be true. So you get 2 equations. We got a subsequent question here. And it just came down to the fact that they didn't put the plus sign here and should have. Okay, so that definitely should be a plus. So you have the I component because it's like the person that caught me on that one.